In this problem, I wanted to talk about the resonance of a transverse waves. In the figure that I will show after I read the problem, there is a wave that's generated on a string, and the pattern that's produced is a standing wave pattern. The string has a mass of 2.5 grams and length of 0.8 meters, and the string is under tension of 325 newtons. So the question is, what's the wavelength of the wave on the string? What harmonic number n corresponds to that wave? What is the frequency of the wave? And then what is the maximum magnitude of the transverse velocity um at coordinate x equal to 0.1 meters? And at what point during the element's oscillation is the transverse velocity maximum? So here is the standing wave pattern. So the wave propagates to the right, reflects from the fixed end on the right side of the string, propagates to the left. The two waves interfere with each other and create this standing wave pattern. So I can calculate the wavelength of this wave by just identifying how many wavelengths fit on the length of the string itself. So here is my standing wave one more time, generated by the interference of the two waves, one going to the right, one to the left. So each branch here of the standing wave pattern is equal to lambda over 2, or corresponds to half of a wavelength. And so the total length of the string is L, so therefore I have 4 times lambda over 2 fits the length of the string L. So lambda is equal to L divided by 2. I know the length of the string, which is 0.8 meters, so I can calculate the wavelength. So lambda is equal to 0.8 meters divided by 2, that is equal to 0.4 meters. So how do I calculate, or how do I figure out the harmonic number n? Well, there's two ways. One is to use the formula that relates lambda and L, the general formula that I used before. And so that was that lambda n is equal to 2L divided by n. And so let's do that. So n is equal to 2L divided by lambda n. So that is 2 times 0.8 meters divided by 0.4 meters. And so this is equal to 4. There is another way to figure out n, and that is the number of loops of the standing wave. So here we have 4 loops of the standing wave. And so that is also the value for the harmonic number n. So n is in general equal to the number of loops in the standing wave. To figure out the frequency of the wave, I will use the relationship between the speed of the wave, the wavelength, and the frequency. So V is equal to lambda f, and from here f is equal to V divided by lambda. The first thing that I need to do before I can do that calculation is find out what's the speed of the wave. So the speed of the wave is equal to the square root of the tension divided by linear mass density. I know the tension, but I don't know the linear mass density. However, I know that the linear mass density is the ratio of the mass of the string to the length of the string, and I know those two. So I can rewrite the formula as T divided by M over L, or that's a square root of T times L divided by M. Substituting the values for the tension, the length of the string, and the mass of the string, and the formula gives me that the speed of the wave is 322.49 meters per second. Now I can calculate the frequency of the wave. Substituting in the formula for the frequency, V divided by lambda I get that the frequency is equal to 806 Hertz. So to find the transverse velocity, remember that for a standing wave, the resultant wave is described with this equation, with this waveform equation. And so I must take the partial time derivative of this expression to find the transverse velocity. So the transverse velocity as a function of position and time is equal to dy prime dt, which is d dt of twice ym sine of kx times cosine of omega t. So only the cosine term here will get differentiated. And so as a result, I get that this is equal to minus 2 times ym sine of kx times sine of omega t. And of course, I will have an omega here as well. So, right like that. So omega is 2 pi times the frequency, which we found out, so that is 2 pi times 806 Hertz. K is 2 pi divided by the wavelength lambda, which we also found, so K is 2 pi divided by 0.4 meters. And we want to find the amplitude of the transverse velocity at x equal to 0.18 meters. So the one thing that we need to figure out is what's the value of ym. Well, so if we look back at the standing wave picture in the figure, we know that the maximum amplitude is at the antinodes. And so the amplitude is 4 millimeters. 4 millimeters. So that means that 2 times ym is equal to 4 millimeters. That's the maximum amplitude when this sign here is equal to plus or minus 1. And so from here, ym is equal to 2 millimeters. So now I have everything I need to be able to calculate U of m. So U of m is equal to absolute value of minus twice ym omega sine of kx. So substituting everything in this expression and calculating the result, I get that the amplitude of the transverse velocity is 6.26 meters per second. Finally, the last question was, when is the amplitude of the transverse velocity the greatest? And so this now can be answered by analogy with other simple harmonic motion events that we've discussed. For example, a mass attached to a spring oscillating left to right and then right to left. We know that at the two extreme points of the oscillation, the velocity is 0, but going through the equilibrium position, the velocity is maximum. So the same applies here for the string as it oscillates. At the antinodes, the speed of oscillation at the very peak of the wave is 0, because at that particular instance of time the string is not moving up or down, it's stationary. But as the wave passes through the equilibrium position, where the string passes through equilibrium position there during the oscillation, then the transverse velocity of a string element there would be the maximum. So the transverse velocity amplitude is maximum when the string element passes through the midpoint of the oscillation. So right here, U of m is maximum.